Hi everybody, this is Miss Maneely, and I'm here to give you a quick review of functions. A function is a special type of relation. Let's go back to talking about what a relation is. A relation is simply a mathematical mapping or pairing of input values with output values. The domain then is the set of all of the input values for a relation, and we usually represent it with the x variable. The range is the set of all of the output values for a relation, and we often use the y variable to represent those output values. A function is a type of relation where there is exactly one output for each input. A relation is not a function if an input has more than one output. And so if we're talking in terms of x and y, if you look at a table of values, for example, and you see that the x value of 2 produces an output of 3 and also an output of 5, then it's not going to be a function. You want to make sure that all of your x values are unique. The y values are allowed to repeat, but the x values aren't. So in example 1, you're basically given 3 different relations where you're given a set of input values and a set of output values. And in the first 2 examples, it's a literal mapping of the input onto the output. And then in letter C is your more familiar table representation or numeric representation of a relation. And so you're asked to identify the domain, the range of each, and then also determine if the relation is a function. I'd like you to go ahead and press pause and take a minute to go ahead and complete exercise 1. Okay? So just to kind of give you another understanding of the mapping in letters A and B, when you see something like this where we've got an input value of -3 and it maps onto an output value of 3, that's the same as the ordered pair. Let me scoot this over a little bit. That's the same as the ordered pair -3, 3. And notice in the next example, that would be the ordered pair 1, -2. But notice that 1 also maps on to +1. This is an example where our input values have more than one output value. And that defies our rule for functions. So the domain, and notice that I'm using set notation. These are the brackets, and the brackets simply enclose all of the values in our domain. And so all of our domain values in letter A are just our input values, -3, 1, and 4. And then our range is going to consist of all of the output values. And I went ahead and put them in numerical order, smallest to largest. This, again, is not a function because the input value of 1 maps onto 2 outputs. In order for it to be a function, it can only map onto 1. In letter B, we've got our input values. This is our domain right here, -3, 1, 3, and 4. And again, I keep it in numerical order. The output, -3, 1, and -2. Now in this case, each of my x's, or each of my input values, has its own output value. Notice that 1 and 3 both map onto an output value of 1. That's okay. That's allowed because the 1, as my input, has a unique output of 1. And 3 also has a unique output of 1. That was different in letter A. The input value of 1 did not have a unique output. It had 2. It had a -2 and 1. So example B is a function. In letter C, now it's a literal mapping. This is what you're traditionally seeing is your ordered pairs. So we've got -3 maps onto -27, -2 maps onto -8. So all of the values for x correspond to our domain. All of the values for y correspond to our range. And they already are in numerical order. Since none of the x values repeat, I know this too is a function. Graphic representations. A relation and a function can be represented by a set of ordered pairs, expressed x, y. To graph a relation, plot each ordered pair in the coordinate plane. So for example, if I wanted to plot the point 3, -4, the 3 represents my x value, the -4 represents my y value. And so I want to go over on the x-axis to 3, and then on the y, I'm going to go down 4. And that's how I can plot my point. Just a quick review of your coordinate plane. When we talk about quadrants, This is what we call quadrant 1. This is where both the x and the y values are positive. This is quadrant 2. This is where the x value is negative, but the y value is positive. This is quadrant 3. And this is where both x and y are negative. And then this is quadrant 4. So x is positive, but y is negative. And remember on our coordinate plane that our x-axis is the horizontal axis, and our y-axis is our vertical axis. Okay. So in example 2, you're essentially asked to graph each of the problems or each of the examples from example 1. And so what I'd like to do is give you a second to pause the video and then to go ahead and plot each of these points and then determine if you can figure out a rule to look at a graph and know graphically if the relation is a function. So again, please go ahead and press pause. Okay, so I've gone ahead and I've constructed scatter plots or plots for the relations in letter A and B. And so what we want to do is just note, if you remember from the previous example, we said that letter A was not a function, but letter B was a function. And so we want to be able to tell graphically whether or not a graph represents a function. And so if you remember our definition, we said each x has to have a unique y in order for it to be a function. Well, for my graph that doesn't have a function, notice that if I were to draw a vertical line, right here, you can see that it actually crosses the graph twice. And in order for a relation to be a function, it can't do that. I have to be able to draw a vertical line anywhere in my graph, and it must only cross no more than one time. And so that's another example of why the relation in letter A is not a function, but the relation in letter B is. No matter where I draw a vertical line, it's never going to cross the function more than one time. Oops. So every time I draw a vertical line, it's only crossing one time. And so that means it is a function. And this is called the vertical line test. The third example, you'll notice that I have the same grid as all the others, but the points that I need to plot go off the map. So this is the time when you might want to consider rescaling your axes. So I need to make sure that I can plot a -27 on the y-axis. So if I think about it, 1, 2, 3, 4, 5, 6. So if I count by 5s, I'll be able to plot a -27. And so if you are going to change the scale on an axis, you only need to show 1 or 2 marks to indicate what the scale is. So by doing this, I'm indicating that the scale on the y-axis is counting by 5. So if I wanted to plot the point -3, -27, so -3, I'm not going to worry about the x-axis. I'm going to keep that at, well, actually, no, I guess I need to make it, no, I'm good, sorry. So my x-axis, I'm going to keep it the way it is, so that's -3. -27, well, that's -5, 10, 15, 20, 25. So -27 is somewhere down here, and I'm going to have to estimate. -2 is going to map on with -8, so that's going to be -5. 8 is going to be somewhere over here. I've got -1 and -1, which is going to be a little bit harder, and then I've got 0 and 0. And so if I take a look at these 4 points, so no matter where I draw a vertical line, it's never going to cross the axis more than one time, so this is a function. And again, that's what we call, looking at the graph, the vertical line test. So again, if a vertical line passes through a graph more than once, then it's not a function. Whoops. Okay. Now, all of the graphs that we've seen are considered what we call a scatter plot. Obviously, a relation and a function can also be written with an equation. And so in that case, we'd have a smooth curve or a line instead of a series of points. Example 3 is just a realistic application. So it says we're given the ages and diameters, of several pine trees in the Lumbreck Falls in Canada. So based on the scatter plot, would you say that the diameter of the tree is a function of the age? And in this case, I think it's pretty clear to see, if I draw a vertical line there, it crosses more than one time, and so this can't be a function. It doesn't pass here, it doesn't pass here. But I only need to have one example of it not passing the vertical line test. Okay, so the diameters are not a function of their ages, and that's because the graph does not pass the vertical line test. Okay. So we also want to talk about the symbolic representations of functions. So we've talked about the graph, we've talked about the tables, but now we want to talk about the symbolic representations when we actually use an equation to represent a function. Many functions can be represented by by an equation in two variables, such as y equals ax plus b. An ordered pair, xy, is then a solution of an equation if the equation is true when the values of x and y are substituted into the equation. And so in this case, what you'd want to do is plug the x value of 2 in for x in this equation, and the y value of -3 into the y value, the y variable in this equation, and then simplify both sides to see if the equation is true. So go ahead and press pause and take a moment to do that. Okay, so in letter A, if I plug in -3 for y and 2 for x, and simplify the right-hand side of this equation, I end up with -3. And since -3 is equal to -3, I know that this ordered pair is indeed a solution to this equation. If I plug -5 in for x and 1 in for y and simplify the right-hand side of this equation, I get -17. -17 is not equivalent to 1, so -5, 1 is not a solution. The same is true with letter C. When I plug in 4 for x, I don't get a result of -1. Function notation. Oftentimes, instead of writing y equals an equation, we'll use function notation. And all we're doing is calling the function or calling the equation by a different name. Linear functions, and any function, can also be written using function notation. I have linear functions here, but any function can be written using function notation. By naming a function, and we can use the letter f, for example, we can write the function y equals ax plus b as f of x equals ax plus b. So this notation that you see here is not multiplication. And sometimes you really have to understand the context of the situation to be able to tell the difference, because a lot of times when we're using parentheses, we do mean to use multiplication. But this is an example of function notation, and the way we say it is f of x, and it basically means my function's name is f, and x is the variable I'm using in the function. It's my input variable. And so notice that it's the x that's being used in this particular equation. F of x is just another name for y, and we can use other letters like g or h, and I don't have to use the variable x either. So if I wanted to model like height over time, I might use an h, and then my input variable would be t. So I could say h of t would represent the height of an object over time. So in number 5, you're simply asked to write the equation in function notation. All you're doing is taking the y and replacing it with f of x. And that's now written in function notation. The nice thing about using function notation is that it's a little bit easier if we want to evaluate the function for different values. So evaluating functions is essentially when you're substituting in a value for x into the equation and then simplifying it. So for example, let's say we're given a function, and notice here I'm not using f of x, I'm using g of t. And notice that it's the t variable that's within my equation. So g of t is equal to 3t minus 8. If I want to evaluate the function when t equals 0, then I'm just going to use the notation g of 0. Whatever goes inside those parentheses is what I'm going to replace with my variable. So I'm basically just replacing my t with a 0. And when I do that, I'm simply going to evaluate the equation. 3 times 0 is 0, minus 8 leaves me with -8. So g of 0 equals -8. And this is equivalent to the ordered pair 0, -8, because 0 is my input and -8 is my output. So what I'd like you to do is evaluate each of the functions in number 6 with the given values. And note in letter C that instead of replacing it with a number, we're replacing it with another expression. Don't be intimidated by that. All this is telling me to do is to replace the x with the expression n plus 1. So go ahead and press pause and give it a try. Okay. So if you've done it correctly, When you evaluate f of x with a 3, so f of 3, we're replacing the x with a 3, and we end up with 6 plus 1 is equal to 7. So the ordered pair 3, 7 would be a solution to this equation, or to this function. In letter B, this is what we call a quadratic equation, or a quadratic function, because we're dealing with x to the second power. Don't forget, if I want to evaluate this function at -2, I must put -2 in parentheses before I square it. Otherwise, I'm going to end up with a -4, because the calculator won't know to square the negative as well as the 2. And so when we simplify, we get -14. So the ordered pair associated with this would be -2, -14. Now, in letter C, this is a little bit different because we're not plugging in a number for our variable. We're plugging in another expression. And so all I'm doing, again, is just replacing my x with n plus 1. Notice that I'm using parentheses here because I want to make sure that I'm replacing all of x. And when I plug in n plus 1, now I've got to follow my order of operations. I can't really simplify what's inside my parentheses. So I go to the next step, which would be dealing with exponents. But I don't have any exponents, so now I'm going to move to multiplication. Since I'm multiplying the quantity by -1, I need to make sure that I multiply each term by -1. So that means I need to do -1 times n, and that gives me -n. And I also need to multiply -1 times 1, which gives me -1. I don't want to forget that I still have a -5 hanging out on the outside. Once it's in simplest form, I can go ahead and simplify. And I realized that I forgot to include an equal sign here. So there should be an equal sign before that -n. So when I combine my like terms in this example, my n is still negative, but -1 minus 5 gives me a -6. Okay, that is the end of our video on functions, or introduction to functions. The next video in the series relates to function operations, and so you should watch that next.